number. Okay, so this is section 3.5, number 9. And so it says, prove that every line through the origin in R3 is a subspace of R3. Okay? Prove that every line through, well, since we're in R3, the origin is 0, 0, 0. In R3 is a subspace of R3. Now, one thing that makes this difficult, I think, is you have to know how to represent a line in R3. Although the first day of class, I remember we passed out these cards and we showed you different ways you could talk about lines in R3. Okay? So some of that may come back. But then the second thing is, okay, what about a subspace? Okay, so there's kind of two things I need to do. I need to know a line through R3, what it looks like, and I need to know a subspace. And so let me pause and ask, do you guys have any input into how I should represent, first of all, a line through R3? Interesting you say that. Way back the first day of class when we talked about lines through R3, one of the things I mentioned to you guys was called a direction vector. Remember that? You need a direction vector like ABC or something like that, I'll call it. And you also need a point on the line. And so basically what we did, let me show you what we did. We had parametric equations. The parametric equations of a line look like this. X equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. But then if you understand in terms of vectors, the fast way to write that is xyz is equal to x naught, y naught, z naught plus, well, t times the direction vector. Okay? So the point on the line is just this initial x naught, y naught, z naught. The direction vector shows up next to the parameter. Who's with me so far up to here? We did this, right? So now, what point do we have on our line? 0, 0, 0. So for us, the equation's even easier. For us, you know, if you want to really use vector, you could write x equals tv, where v is my direction vector, and then x is just kind of my variables. So I agree when Noah said, hey, a line through the origin is just a span of the vector. Yeah, I get that. As a matter of fact, if you think about how do you prove it's a subspace? Well, we need to check three things, right? To prove that it's a subspace, there are three things to check, right? So first of all, let me go ahead and work it out. Let L be this line through the origin. Which one? Well, I'm going to represent it this way with that purple equation. Okay? So what are the three things I need to check? First of all, I need to check, is 0 on the line? Well, yes. Just let t equal what? 0. And then 0 times that vector is going to be the 0 vector. So is the 0 vector part of the line, right? By the 0 vector, you guys do know I mean this, right? Yeah, they even said it's a line through the origin.
Let L be?
Let t equal 0 and you have it. So,
let L be what?
oh, a line through the origin. This line, x equals TV. So what are the other things we have to check? We have to check that it's closed under, so is L closed under what? Addition, yep. That's the next thing. And then what's the last thing you need to check? Is L closed under what? Scalar multiplication. That's the question. So, how would I do that? Well, suppose x1 and x2 are on the line. Those are two vectors. That's why I tried to put these little arrows up there. Okay? Say x1 is equal to t1 times my direction vector, and x2 is equal to t2 times my direction vector. Because everything on the line is going to be something times that direction vector. Now, how do you check that it's closed?
X1.
We're going to take x1 and add it to x2 and see what we get. So we get t1v plus t2v. And then what do? You write that as t1 plus t2 times v, and that's a number times v. So yes, I would say yes, we just showed it's closed under addition. And I would say that that's probably enough that you guys can check that it's also closed under scalar multiplication. Okay? I think the hard part of this problem is both understanding what it's asking and understanding maybe an efficient way of checking. And here's where this vector notation is really kind of a clean way to do it compared to lots of other ways you might try to represent the line. So, kind of shows the power of linear algebra, I think. It's a good problem. So how do I prove number 33? Well, what's the given? Got to start with that, guys. What's the given?
Given number 33.
Yeah, matrix R is in echelon form.
Given is what?
Matrix R is in echelon form. You got this one on your homework, Mike, I saw. And then, what are we trying to prove?
I'm done with number 33 already?
Yeah, I saw it, yeah.
Oh, you helped me out?
Mm-hmm. So then it says down here, a basis for the row space of R consists of the non-zero rows of R. That's what we're trying to prove. So that's going to be the last statement. All right, I'll try and help you do that. So here's my proof, right? That's my given. Way down at the bottom, let's write, well, a basis for the row space of R is given by the non-zero rows of R. Now, how do you show that the non-zero rows of R are a basis? This is what I call kind of unpacking. That's the vocabulary word you need. Do you guys really know what a basis of a subspace is yet? And I claim there are two things you need for a set of vectors to be a basis. Ask the person next to you if they know. So guys, if we want to prove that the non-zero rows of R form a basis, there are two things I need to check. Do you guys know what they are? Either one of them?
In the span of row R, and they are linearly independent.
So I'm going to put the second one down. They are linearly independent. And that one I think we understand pretty well. The other one is kind of newer. The non-zero rows of R span the row space of R. They have to span whatever it's a basis for. That might be a little bit tougher. Okay? So, let's see. How about this? Let V, which is
Top or the bottom?
capital V here at the top. Let capital V be V1, V2, etc., up to VK, be the non-zero rows of R. Okay? By the way, I think when I'm doing the proof here, it's helpful if we have an example. So let's go back to matrix A.
Not zero what?
Oh, sorry. The non-zero rows of R. But again, you have this on your homework, Mike, so I don't want to slow down. So here is matrix A, right? That doesn't work because that's not in row echelon form. R is supposed to be in row echelon form. So why don't I make my example be this? Is this okay for an example? All right. So do you guys understand what I mean by V for our example? How many vectors are in V for my example? Just 2, right? The question is, do those vectors form a basis for the row space of A? Now the row space, of course, is the set of all linear combinations, right? So, do they span the row space of R? Well, I claim that this is true because adding on the 0 rows would not give me additional vectors. Do you see what I'm saying? The row space is the span of these 3 rows. But if you think about it, the third row of all zeros just doesn't help, right? I mean, if you write C1 times the first row, which is 1, 0, negative 1, plus C2 times the second row, which was 0, 1, 2, if you add the third row on, does that even help? No, because the third row is a bunch of zeros, right? So I claim that this is true. The non-zero rows span the row space of R. Now, what about the second one? Do we know that the non-zero rows of R are linearly independent? Well, yeah. How do I know that? Because normally, how do you check to see if rows are independent? You put the matrix into what? Row echelon form, right? Like if I go back to here, is matrix A, are the rows of A linearly independent or dependent? For matrix A, they're dependent. But for matrix R, guess what? They're independent, right? So I would say the reason that this is true because R is in
the second or the first one?
echelon form. So I did both. The red is my reason for the second fact being true, and then up above, the dark blue is my reason for the first fact being true. So I claim that gives you a proof that takes care of this problem, what was it, 33? In section 3.5. Hopefully that helps.